Video 17 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is density matrices, and it's in a way a continuation of chapter 2-3. So if you can't remember that, please go back and listen to this lecture before listening to this lecture. We want to look now at the expectation value of a spin-free one-electron operator. A one-electron operator means that the operator is a sum of operators acting each one only on one electron. And here, for a change, I want to write out this expectation value not only in the Dirac notation as here, as we've used, but actually write it out in the integrals. And since we are looking at a system with n electrons, this is a 4 times n tuple integral where we have to integrate over the 4 coordinates, the free spatial and the spin coordinate of the n electrons. Now, electrons are indistinguishable, and therefore each term in this summation here, so whether it's electron 1, 2, or 3, they all give the same result. And therefore, instead of having summing here over the n electrons, I might as well just look at the integral with the operator just for one electron, and for convenience I use electron 1, and then multiply the result by the number of electrons. Now we assume that we're looking at a spin-free operator, and therefore I can integrate now the spin out, which means that after spin integration then I only have here the 3 spatial coordinates for every electron. Now I want to make use of the reduced one electron density matrix before here in this integral. But before I can do that, I have to rearrange the kernel of the integral a bit. So I have to move the operator out between the two wave functions. Normally, of course, in expectation value, the operator is sandwiched between the complex conjugate of the wave function and the wave function. So what I've done here now, I've moved the complex conjugate from here standing in front of the operator over to the right hand side. Now I have to be careful on doing that, because if this operator here just includes the position vectors of the electron, then there's no problem. But if it includes any kind of derivative with respect to the position of electron 1, then of course I would have a problem if I move the complex conjugate of the wave function here to the right, because then this operator is not going to apply to the wave function here, but also to the complex conjugate of the wave function, which of course is not correct. This would give some different results. Therefore, one uses a small trick, and the trick is that one changes here the variable for electron 1 in the complex conjugate of the wave function. So instead of having R1, and this is acting on R1, we change this to R1 prime. And then we let the operator act on here on the wave function. And after this is done, so after I've taken the derivatives, if this operator includes a derivative with respect to the position of electron 1, I change this R prime 1 back to R1, and then I integrate. So this is sort of what this superscript on the integral is trying to indicate, that before integration, after applying of the operator to the wave function here, but before integration I have to replace R1 prime with R1. Now I'm ready to use the expression 222 from chapter 2-3 with or introduce the reduced one electron density matrix. Now what I really want to do is to look at the case where we have an external electromagnetic field. And of course, in the presence of the external electromagnetic field, we have now a field-dependent wave function, a perturbed wave function, and therefore also our electron density and our reduced one electron density matrix become field-dependent, because they both include the wave function, and the wave function is now field-dependent, and therefore also the density as well as this reduced one electron density matrix become field-dependent. And like we've done several times in the last few lectures, I can expand these field-dependent properties in the perturbation series, in the power series. And here for the density, I have the field-dependent density. And here I have the unperturbed one as the zeroth order term. And then I get the first order, second order, and so forth correction. And here I've written the first order correction up. And I write it a bit different than we've done it with the wave function, because I immediately split it up in the component of the fields and what essentially is the derivative of the first order correction to the density matrix, which I call here P alpha first order. And in the same way, I do it here for the reduced one electron density matrix up to the first order, and again split it immediately up in the field, and this essentially first derivative of the first order correction to the reduced one electron density matrix. And how do they look like? Well, of course, if I insert the expansion of the perturbed wave function here in the expression for the density and collect all the first order terms, and then make sure then I get as this P alpha first order, I get the sum of those two integrals, where here I have the derivative of the first order correction to the wave function, my density operator, and the unperturbed wave function, and here the interchange on where I take the derivative in the cat instead of the prom. And similarly, I get the first order corrections to the reduced one electron density matrix by having the derivative of the first order correction to the wave function here or here in the complex conjugate. So I get those two terms. Now let's get to our expectation value of our operator. So the first order correction to the expectation value of our spin-free operator, I can also write now with this first order reduced density matrix. The first order correction would be, of course, where I have first order correction in the ket and the first order correction in the bra of the wave function. And with respect to the first order reduced density matrix, I simply can write it as this term, an integral over just one electron, our operator, and our first order reduced density matrix.